Okay, so I'm just going to start by copying down the first question. So this is exercise 11. Which is let R and S be two rings and theta and S be a ring homomorphism. Okay, so part A is to prove that theta 0R equals 0S. So I'm going to start by using one of the definitions for ring homomorphisms, which is theta A plus B equals theta A plus theta B. And then I'm going to let A and B, in this instance, be 0R. Okay, so I'm going to rewrite this as theta 0R plus 0R equals theta 0R plus theta 0R. Okay, so I'm going to first simplify the left-hand side, because anything plus the additive 0R is going to be 0R, as this is an additive property, and 0R is the identity element. So that will just become theta 0R equals theta 0R plus theta 0R. And then I'm going to use the additive inverse, which is subtracting. So I'm going to minus theta 0R, which is the inverse of theta 0R, from each side. And then to simplify this, as theta 0R is the additive inverse, then this will just become 0, and same on the other side. So that will become theta 0R equals 0S, which is the proof. Okay, and then part B, now to prove that for all R in R, theta minus R equals minus theta R. Okay. So I'm going to start by using the same definition as in the first section, but this time I'm going to assign A to be R and B to be minus R. So I'm just going to write it down like that. Okay, and then as R and minus R are additive inverses of each other, then the left-hand side is just going to become theta 0, if I simplify it, 0R. And then the right-hand side is going to stay the same. And then I'm going to use the additive inverse for theta R, which is minus theta R. And I'm going to subtract minus theta R from both sides. That's not right. Lowercase r, I meant. Okay. And then as theta 0R, as I showed in part A, that is just equivalent to 0. So the left-hand side just becomes minus theta R. And then the right-hand side, as theta R and minus theta R are additive inverses of each other, they're just going to become the additive identity, which is 0R. So that is just going to become theta minus R, which is what I was trying to prove. Okay. And then exercise 25 is next, which is to prove that if, I think it's psi, the symbol, probably pronouncing it wrong, is a ring homomorphism, I think I spelled that right, then psi an I'll try it down here. Is an ideal of R. Okay, so from the module booklet, I know that psi, the set psi is equal to R in R is equal to 0. Okay, so I'm going to prove exercise 25 using theorem 5.1 from the booklet. And the first step is to prove that the set psi is not empty. So start with saying that 0R is in the ring R, and then psi of 0R is equal to 0s, shown in exercise 11a, and then 0s is in psi, the set, so therefore the set is non-empty. Okay, and then I'm gonna skip down to the next page, I think. And then the next step in theorem 5.1 is if A and B is in the set, then A minus B is also in the set. So to prove this, I'm going to use the same definitions I did in the other ones. So I'm going to have, let me set it up first properly. So let A and B be in the set psi, then psi A equals 0 and psi B equals 0 for some psi A and psi B in R. Okay, so then using the definition I mentioned I was going to use a second ago, I have psi of A plus psi of A minus B, which is the equivalent to A plus minus B, which means that the right hand side is going to be psi A plus psi minus B from the definition. Okay, and then using part B from exercise 11, I know that psi of minus B is the same as minus psi B. And then using my first line, I know that psi A and psi B are both 0. So psi of A minus B equals 0 minus 0. Which is equivalent to 0 as it's the identity, subtracting it, and it's just 0. So I've got that. And then, therefore, A minus B is within the set. Is within the set as 0s is in the set. Okay, now I'll do the third bit. Okay, so I'm going to let A be in psi and R be in R. And then psi of A equals 0 for some psi of A in R. Okay. So for part 3, I need to prove that if S in the set and R is in R, then SR and RS are both in S. So I'm going to start this with psi AR equals psi A psi R from the definition, which is the equivalent to 0s dot times by psi R for multiplication. And then anything times the identity is just going to be anything times 0s, it's just going to be 0s. This is going to be equivalent to 0s. And then and I already know it's going to be the same for RA because of is it commutativity, I think. But then I'll just write it down anyway. So to show that they are equivalent, and therefore RA and AR are both in the set per psi. And then as all these three things I've shown, that means that therefore the set per psi is an ideal of R by theorem 5.1.